made a cheap garage door opener. That way, any family could purchase it without spending too much on having something that's essential for their home. So this design is meant to cater to those that are looking for a simple design without any complicated features. This design must not make any compromises when it comes to safety. That's probably my uh, biggest key thing that I follow to make sure that it's as safe as possible. So I also added another security measure. I added a timer that causes the garage door to automatically close when it is set. And I wanted to reduce the size as much as possible to save in manufacturing costs. So it shouldn't take up too much room. So in the slide, I have my state and input condition, my states and input conditions. I have a total of 5 states. I call them G0, G1, G2, G3, G4, G5, and they're labeled accordingly. I have 8 input conditions. My first one, B1, refers to the pressing of the main garage door button. T refers to the switch that is used to set the timer. DC refers to the our input from our sensor, checking to see whether or not the garage door is closed or open. O refers to the input from the sensor checks to see if there are any obstructions, and OC refers to the input from the sensor that continually checks to make sure that our obstruction has been removed, whether that's a person, an object, anything like that, an animal. LC refers to our limit switch that is set when our garage door is closing. I'll talk a little bit more about that when I get to that on my ASM chart. LO refers to the same thing, but when the garage door is opening. And H refers to the hour that the timer sets. Okay, so, and then our outputs are just D. D is our garage door sensor, M is our motor, and then RM stands for reverse motor, which is when the output closes the garage door. And then I just have a small picture that I made of my actual garage door, what I imagine it would look like. So it's very basic, probably to save on costs. But again, if I were going to save on manufacturing costs, I want to make sure it's as simple as possible without it being too complicated. So I have a large, the garage door button is on the bottom, which is the kind of, I don't know if you can see my mouse cursor here. This button here is the main garage door button. And right here is my switch to turn my timer off and on. And this little picture here is just a clock, just to tell you that it's a timer. So I have my ASM chart. These two are the same, just that the one on the right has small descriptions to make it a little bit easier to follow. And my left one doesn't have a lot of those descriptions. So just to help you guys follow along with my chart, I'm gonna go with the right side. That way it's a little bit easier to visualize how my garage door system works. All right, so we're starting in my first state, G0 or 000, which is my idle state. So I try to make this design cyclical, where it would go to my idle state where it isn't outputting anything, and it's whether or not the garage door is open or closed. In this state, my garage door system is not doing anything at all. So for my first conditional statement, I have my button press, whether or not that is true or false. So as long as it is false, it's going to stay at its idle state. So that means my user has not pressed the button. My user is not interested in working the garage door. So for obviously, we're going to assume that they have pressed the button. We are going to go to our next conditional statement, which is our timer switch, and whether or not that's true or false. For now, we're going to assume that it is false. They have not set their security timer switch. So we will get back to that at the end. just to see how it deviates from our main kind of section of the chart. So if the timer switch is not set and it's set to false, our button, it would go to its next state, G1001, which states that our button has been pressed and our door sensor activates. Our output is our output goes to our door sensor. So in that state, and I kind of added that red like square to help you guys or to show you guys where exactly we are on the ASM chart. So we are currently in G1. So the button been pressed and our garage door sensor is activated. So we have our next conditional statement. It's going to ask whether or not our door is closed. So we're going to get an input there telling us whether or not this door was already closed. And it, in order to make it a little bit less complicated, I'm going to go straight to state 3, which is starting the cycle to open with the motor. So we're going to output to the motor, and then we'll go down to state 2 because that one gets a little bit more complicated, especially with the safety features that I have added onto it. And then here we have a picture of my garage door sensor. These are attached to the sides of the garage door to yeah. All right then. So now we are in this state where we have the cycle to start opening our garage door. So our first input condition is going to ask again whether or not our user presses the button. So that's kind of a security feature as well. Let's say our garage door is opening and they decided, wait, I don't want to open it. I accidentally pressed it for whatever reason. They are able to press the button again, which would take it to state, as you could see here. It'll go, if that's true, they do press it again, it'll go to state 2 to start the cycle to close. But in order to keep this going, we're just going to assume that they have not pressed it and that they want the garage door to open fully. So then we go to our next conditional statement here, which has the which asks, has the garage door reached its set limit switches? So with the motors, there's a thing called set the limit switches that can be set by the manufacturer, or it can actually be set by the user. Although, unless you're a professional garage door installer, it's not recommended that you mess with those because they are preset for the most part to make sure that the garage door doesn't open too much or keeps on going once it's actually closed. And I'm just going to skip ahead and then I'm going to go back to this slide just to show you guys what it looks like on a LiftMaster. Right there, we can see that this user is kind of changing their limit switch, but again, it's not advised to for safety reasons, obviously, unless you're a professional. So where were we? So our button press is false. Our user has not pressed the button again. And if the garage door has not reached its the set limit switch, that is also false. That would also be false, and it would continue, go back to state 3, and it would keep on having our garage door open until it is true it has reached its set limit switch. Once that is true, it'll go back to idle. So what that means is that it'll keep on cycling through, keep on opening until it reaches its set limit switch, and it'll go to idle, and it would stay open. So it won't do anything else. It'll just open all the way, and once it's at idle, nothing else happens. It's just going to be static, waiting for its next input from the user. Okay, so for our next state, our state 2. So let's say our garage door was open. Instead of it being closed, which would be false, we would go to our state 2, which is G2010, and that is start the motor cycle to close. So we're starting our cycle to close. And again, we have the same option as that it has when it is opening. And that's saying whether or not our button has been pressed. So maybe our user decides, maybe they see a family member coming in with their vehicle, or they see somebody running towards the garage door and they don't want it to close on them, which again, I'll talk a little bit further. There's a security measure that will prevent that, but let's say they see somebody walking through or a car coming through, so they want to, instead of closing it, they want it to reverse and go back to opening the garage door. It will go to back. If that's true, it would go back to our state 3 and then begin our cycle to open our garage door until it reaches set limit switch and so on. But in order to keep this keep us going, we're just gonna assume that it is false. Our user just wants to close the door. They don't have any other worries. So then we go to our next conditional statement. In that case, we go to ask, are there any obstructions? And we ask whether or not that's true or false. So right here, we're gonna assume that yes, it's actually true. Maybe a child left their bike underneath the garage door. A child runs through at the last second. Let's say maybe an animal, a cat, ran through the garage door. So our garage door sensor is going to sense that. And if that's true, it's going to stop our motor. This is our next state, G4, 100. So at this state, our motor is stopped. And now we're going to output to our door sensor to continually check to make sure that our obstruction has been removed. So we could see here that it's asking, has our obstruction been removed? And if that's false, we are going to go back to our state 4, and we're going to continually keep on doing that. We're going to make sure our motor is stopped until that that obstruction has been removed, until that's true. And if that's true, we're going to go back to state 2, actually. So we're going to cycle back to state 2 to check to make sure our motor cycle, to start our motor cycle to close our garage door. And again, it's going to go through the same safety checks. It's going to check to make sure our user doesn't want to, let's say, open it back up again. And it's also going to check to make sure there aren't any more obstructions. So maybe another cat comes through or anything like that. So it's going to continually check to make sure that there aren't any obstructions, and it's going to close our garage door accordingly in our state 4. But if, let's say, there are no obstructions, we're giving the all clear, and that is a false. We are going to go up, and then we have another limit switch. This time it is to close our garage door. And as long as that input is false, we are going to go back to our state. So that means our motor is not going to stop. It's going to keep on closing until it reaches that set limit switch. And it's going to continually keep on checking to make sure there aren't any obstructions or any further obstructions until it is fully 100% closed, until it reaches that limit switch, which again is why it is not recommended that you mess with that unless you're a professional or or you're the manufacturer, because obviously the manufacturer is going to know how much our motor should be opening and closing. So that's the great thing about this, is it's going to continually check to make sure that nothing goes underneath the garage door and nothing gets caught in between the garage door, which is a huge safety concern, especially when I have a garage door that doesn't have a sensor. So if you're underneath that, it's going to close on you. So I have to make sure that that we don't compromise any safety features. So let's say our garage door is continually checking, and then it's true that it has reached its set limit switch to close. Then it would go to idle, saying that now that it reached its set limit switch, it's completely closed. It's going to go to idle, and it's not going to do anything further. Everything's off. It's not outputting any signals. It's just going to stay closed, and it's going to wait again for our next command. So now let's say our garage door is already open. So let's say we went through the cycle here, and then we're at state 3, and then we open our garage door again, and then we are in idle. Okay, we'll move on to our next one, which is our timer device. So our garage door is already open, we are in idle, and our user sets our switch up to make sure it outputs true. And they press the garage door button first, and then our timer switch is true. And then instead of going down to state 1, we are actually going to go to our timer device, which is state 5, 101. And what our timer device does is it's going to set an hour limit, And once that limit is done, it's going to close our garage door. But first, we need to go through our conditional statements. So we see here that we have another safety feature in case our user accidentally sets our timer device. They are able to actually get out of that hour-long loop by just pressing the button again, which will take them directly to idle, waiting for the next input. So they could remove the switch and then close it or open it manually. But let's say they set it purposefully to close. And the reason why I added this, because I know I've done this before where I do yard work and I leave my garage door open, and then several hours later, I forget that I have left it open once I finished all my work. And you don't want anybody getting into your garage door. So you want to make sure you have that kind of backup system to help you protect your belongings. So I decided to add this timer for an hour. So once it's false that the button hasn't been pressed and the hour hasn't passed either, which would tell us false, it would continually go back to our timer device and make sure that the timer is powered on. And it's going to continually check until that hour is done. Once that hour is done, it's going to output true, and it is going to go to our state to close, our G2 state. Okay, and then from there, it's going to go through all the safety precautions, everything like that. So it's still going to be safe whether or not it starts closing randomly in an hour. Let's say you were doing yard work and then you forgot you set it and it just starts closing automatically and you're walking underneath it. It's still going to be safe. It's not going to close on you or anything like that. It's going to go through all its safety protocols and everything like that. But you might be thinking, wait, what if you set the timer and the garage door was closed? Well, if there aren't any obstructions and you don't press the button again, it is going to check that our garage door limit switch is true. It's already closed. So it's just going to go straight to idle. So it isn't going to really do anything. Okay, and in this following slide, I have my table where I have my present states. I did these by hand. I'm going to show you the other slide where I made them a little bit nicer. So the present state and my input conditions, I have my next state, and I also have my outputs, D to the door sensor, M for the motor, RM for the reverse motor for it to close. So let's go to my next state. So in this table here, it's a little bit nicer to see. I have my input condition. So for like my present state 000 to go to the next state G000, so back to idle. I would need a not B1, so not a button press or just a false on that conditional statement, and so on. I have it all listed from top to bottom. And then I have my simplified Boolean expression. So as you could see, they're fairly complicated. There's a lot of AND gates, OR gates that are being used, NOT gates, and show you that next. Oh, sorry. So, and then these were simplified to the best of my abilities. It was far more complicated beforehand, but I got it down to something that's at least somewhat manageable, one that you're able to see here. Okay. So for my initial cost, I saw that I needed 3 D flip-flop as well as a crystal oscillator. The flip-flop in question is CD4013B. This device consists of 2 identical independent D flip-flops. So there's 2 in each of them. Even though I technically need 6, in each IC there's 2 of them, so I only need to buy 3 of these ICs. And then you can see here that the cost for each of them is 52 cents. I found it on the DigiKey, I think was the website. And crystal oscillator was 50 cents. I think I found that on Amazon. They had like a bundle or something like that. So I just estimated the cost of just for one of them. And that came out to 206. So that's going to be the initial cost of like all the hardware I'm going to be using or talking about. All right, so for my first hardware that I tried are the logic gates. So using logic gates will make the circuit far too complicated. Just right off the bat, I saw my my Boolean expressions. I did not know how I was gonna. Well, obviously it's possible to do that, but it's far too unreliable. If I mess up on one part of my my design, it's game over. It's not going to work, and to figure out what's wrong with it will make it far too complicated. Or my next state A alone requires about 18 AND gates and OR gates, along with several NOT gates. And then
Yes.
I got, oh, yes?
So I'm sorry, can I just ask, these eyebrows signs, are they the not sign?
Oh, yes. Sorry about that. I should have specified. Yes. Yeah, they are not.
All right, fair enough. Thank you.
Yes. Sorry about that.
So when you put, for example, the very first term, not A, not B, not C, then
Mhm.
you have a bracket. Is that not C and B1?
Oh, I'm sorry. Yeah, I should definitely explain this a little bit better. So this B1, I added that it only says that my input condition has two letters together. They're not ANDed, but this is just a one input condition. So as you see here, I have OC, which is my obstruction checker. That is just one term, one input condition. It isn't two of them ANDed together. It's just one. And I added that just to make it a little bit easier to see. But I have A and B, and not A, not B, not C, not, sorry, not A and not B and not C and B1 and T. Those are my input conditions. So anytime you see a parentheses, I just made that a little bit easier to see because some of my input conditions have two letters as kind of like their names.
Sure. Okay. Yeah. Continue. Yeah. Thank you.
Yeah. Thank you for reminding me about that.
All right. Yeah, I can see now.
Okay, then. So for my logic gate cost, using logic gates can be more costly as compared to our other options. Using logic gates will make my design big and bulky, which adds to the cost of manufacturing the door openers. So I have for my first gate, my 74LS04 NOT gate. I need about 3 ICs, $1.69 came out to. My SN74LS08N, my AND gate, which I need about like 6 of them since they come with I think 4 AND gates, which is $1.65. My SN74LS32N comes out to about 3 ICs, $0.52. And then I have the D flip flop and the oscillators that I talked about earlier, which came out to $9.59. So it isn't terribly expensive, but you're going to see that my other options are a lot better. Yeah, a lot cheaper too. And probably the biggest reason why I would not use logic gates is just the amount of space it would take up. It's unreliability. All right, and then I also looked into the possibility of using a JK flip flop. So an advantage of using a JK flip flop is that it will simplify my Boolean expressions. This JK flip flop example is only for my next state A. So I have it right here on the side in a little picture. You can see how I worked through that. And then we see that using a JK flip flop requires us to still use a lot of gates. And this is counterintuitive to reducing the amount of space my project will take up. That was my biggest thing. I want to make sure I keep it compact. And I don't think I could sacrifice that, especially when I'm trying to sell this design and I bring in maybe a prototype that's way too bulky that takes up most of the table. That's not going to be very attractive, especially with nowadays our garage door openers aren't huge bulky machines. They're very small. I want to make sure I follow that. And then my next hardware is FPGA. So benefits of using the programmable devices include faster design times, fewer components used, and lower cost options. So they don't come out too much, and they're so easy to work with. But of course, it has its downsides. Because it is volatile, it is best not to use FPGA. If there's a power outage or anything like that, my customers would not be happy to find out that their garage door opener is basically trash. It does not work for them anymore. So I decided to scrap that idea. I can't afford to send a technician out there to program it or do anything or to fix it every time a neighborhood loses power, which is often in some states. So we have to make sure we keep that to a minimum. And then there's also the safety concern when it comes to losing power. So let's say you're working on your garage and your garage door is already open and your garage door no longer works. Well, how are you supposed to protect your item by closing your garage door? You can't anymore because of the power outage. And then the FPGA also has large propagation delays, which again just adds it's added to the long list of things of why I shouldn't really use FPGA for something as important as a garage door opener. So my next hardware is using an 821 MUX. So my design requires 6 821 MUXes, which requires 6 flip-flops and requires 1 clock. Several logic gates are also required for the input, which complicates my design. So, of course, for when you're inputting into our MUXes, you're still going to need those inputs. And as you see here, although it might be a little bit hard to see, I'm still going to need several and OR gates and NOT gates into my input here. So you can see that each line here. So I0 it requires B1 and T. So I need to be ANDed, obviously. My next line just requires B, which would be easy to implement. But then when I have all these different inputs, it will still be complicated. And not only that, the addition of extra gates requires us to take more space that we can't afford to give up. And also, there's the additional cost of having to buy more gates. Okay, then. So, and then right here I have just an image of my quick like scratch work of using my AND gates, and my cost for my 821 MUXes. I found one on DigiKey, I believe that was the website. 74HC4051D and 821 MUX, 6 of them. It came out to 47 cents. So I would need 6 of those. And again, my flip-flop oscillator, those are kind of my initial cost. Then my AND gates, OR gates, and NOT gates, I estimated to be around 5, 2, and 1 of them respectively, which came out to a total of $9.86. So it came out a little bit more expensive than just using our logic gates, but it was kind of easier to design than just straight up using my logic gates. And then the additional cost of the gates alongside the MUX makes our design choice, again, less desirable. And then right here, I just have a quick picture of my my Boolean expressions in order for my next hardware, which is PAL. So advantages that come to using PAL is that it's highly efficient. It's low production cost as compared to PLA, which is why it's best not to use PLA. Highly secure. Has high reliability. It has low power required for working, so save on power. More flexible to design. And believe it or not, even though it looks complicated there on the right side, that image here, it was a lot easier to implement. And it's obviously more flexible to design. And the reason why I did not choose ROM, which is a big deal, is that a ROM requires us to include all possible min terms, which would make my design it'd be too much. It'd be very wasteful to do that. So PAL does not. So I decided to run with that. And then we have my inputs here, NOTed, my NOT. And then I have my AND gates, and then those get ANDed, and then they go to my OR gates here. And my PAL cost, so PAL is the most cost-effective option. PAL uses less space, is faster, and is more reliable than just using ICs or my logic gates. I'm sorry. So PAL allows for easy design changes as well, and is not volatile, which is a big thing. I don't want power outage or anything like that to ruin my design. So I have to make sure that I keep that design protected and make sure that something as simple as a power outage doesn't affect it. And then I found a PAL 16R6CN chip for $2.66. And again, the cost of the flip-flop and the oscillator came out to $4.72. And for my final verdict, I decided to use PAL. PAL saves in my programming and manufacturing costs. PAL is superior in ease of programming, reliability, and its compactness. The hardware only costs $4.72, which would save a ton of money as compared to my other options, which were close to double the cost of using PAL. And that is it, I believe.
Any questions from anyone?
I have a question. It's not more like a question. It's just I just want to see how you use your JK flip flop for the.
Sure. There you go.
Oh, okay.
Right.
Nice. I like that. I didn't know you could use JK flip flop too. Yeah, cool. All right, cool.
Right. Yeah, it made it a little bit simpler, but even then, I still require more gates.
Yeah. All right. Thanks.
Yeah, no problem.
All right. I enjoyed this very, very much, Christopher. Thank you very much. I really, really think that you've done a fantastic job. I may be wrong. I have not seen yet any garage door controller, opener, as you name it, that would close after 1 hour. And this is a fantastic feature that you added. As I say, I could be wrong. There might be doors that closes after 1 hour or 30 minutes, but I have not seen one. However, this is a very, very good feature that you just added to your design, which made it that much more beautiful. And I honestly enjoyed your chart, enjoyed your table, enjoyed your logics on how you go from one form of hardware to next. And I cannot add anything to this except for one thing that I need to remind you and everybody else that so far have spoken about PAL. And when you do your cost comparison, you forgot to include the programming cost.
Oh, okay. Yeah, it's definitely something very important.
That is an important thing. I mean, because as a designer, you need to spend several hours maybe to program that PAL, and that should be an added. However, I mean, this is something that neither of you so far have added. It's not that easy either. I mean, how would you then estimate that cost? As a professional programmer, you need to charge, say, $10,000 per hour. And yet, that would be ridiculous. It depends on who the client is, how many they need, at what level. So you're good so far. I mean, so that is what I'm saying. The cost is good. It's just not real. However, it depends on circumstances. And the only minor other comment that maybe with PAL, you don't need those flip-flops. Yeah, they are usually registered output, and you feed them back. Israel, you were going to say something.
Actually, it's a question for you. Would you say it's reasonable to, I don't know, give estimate a worst case amount of hours, and then just, because you could search for programmers and how much they charge personally per hour,
you could
just do a worst case sort of thing, like, hey, this will take 50 hours at $100 an hour, I guess, and then that would be worst case though, that would be the roof, I guess, so to speak.
I guess you see, you have to be more careful here, because that is ultimately what you're going to charge your client. So if you go for the worst case scenario, you'll be out of pocket. So really, and yet you want to win the bid, so you want to get it as low as possible. Really, it's something that I honestly, you can't answer this easily. But I don't believe good programmers, professional programmers that you can rely on and you can give it to them and get them to design to program it so that you can believe in what they did, would charge less than $10,000 an hour. I don't know where this $100 or just like cheap cowboys. I don't know if that's right. So again, I mean, this is something that really you can probably answer just as good as I can. So, right. Anyway, so I enjoyed the state table very much, and I enjoyed the the ASM chart very much, and I liked it how you made a kind of simplified version and yet more elaborative version that is beautiful. That's really, really good. So one thing you need to do, just go back, and when you want to complete your final report, please get all those handwritten in some sort of table, right, written out professionally, and then send me your report. And I'm pleased to say, Christopher, that you're exempt from the final exam because you understood everything you said. You knew how to utilize your hardware. You knew exactly what you were talking about. And therefore, you don't need to take any exam because you know everything. Thank you very much.
Thank you. Appreciate it.
Great. So all I need to ask now is three more. If you would stop the share, please, Christopher.
Oh, sorry.